Okay, thank you, Michaela. Thank you for inviting me. So I'm going to talk about binary black hole simulations with SpEC, and let me first point out that I'm going to talk about only a subset of the numerical relativity work that goes on in our collaboration. I'm not going to say anything about matter simulations, and we've been doing neutron star, and neutron star black hole simulations as part of the our greater collaboration as well, and I'm not going to mention those. I'm going to just concentrate on binary black hole simulations. I was going to start putting a whole bunch of names of contributors up here, but as I started going through the number of names, they started growing very long, so I just shortened it to over 50 contributors, and I will talk about SpEC and say a little bit about that later. So I'm going to start with talking about some motivations for SpEC and some goals, and then I'm going to describe what SpEC is, and for that matter I haven't said what SpEC is. SpEC stands for Spectral Einstein Code, and I will give a brief description of SpEC and how it works, but not go very much into details because that will bore everybody here. Then I'll show a few selected results from SpEC simulations and talk about at the end the idea of constructing binary black hole templates that can be used for gravitational wave detectors. And of course this last thing is something that's not a result, it's something that's you know, in planning and ongoing sort of stage. So first of all, what we want to do is we want to assist gravitational wave detection and parameter estimation by gravitational wave detectors for binary black hole sources by computing templates for use by data analysis. We also want to, independent of LIGO, gain insights into strong field gravitation and black hole systems just by studying analytically or studying numerically these black hole systems. And I'll give you some examples of both of these. So it was realized fairly early on that since there's no analytical solutions for black hole binaries, if you wanted to solve a binary black hole system, you want to solve Einstein's equations and figure out what happens, you really need to go to numerical methods. And people worked on trying to do black hole simulations for a long time, from in the 70s throughout you know, and on, and there were a large number of problems, and the field didn't really get going until a few breakthroughs in 2005-2006, first by Franz Pretorius, who was here at the time, and then later by, very shortly later, by the groups at Rochester, or at that time were Brownsville, and also the group at Baker and et al. At Goddard. So since these breakthroughs, numerical relativity can now solve Einstein's equations for binary black holes, and we're getting into the era where instead of you know, trying to figure out how to get the codes to work, we are able to actually get some results and try to produce waveforms for gravitational wave detectors and so forth. So what's the goal of a perfect, let's say, what would be a perfect numerical relativity code? Such a thing doesn't exist, but what would it be? What would it look like? So what we want is we'd like a solution of Einstein's equations, a method of solving Einstein's equations that is accurate and efficient enough for detection and parameter estimation. And I put accurate and efficient sort of together because in my mind they're essentially the same same thing. You can always obtain further accuracy by throwing resolution at the problem, but if it takes 2 years to run the simulation at the accuracy you need, that level of efficiency isn't going to be as useful as if it takes 2 weeks. So another thing that we want to be able to do is be able to compute many binary black hole orbits. And the reason for this is that we really want a complete waveform, and a complete waveform means that you have thousands and thousands of orbits in the past, and that's usually done using post-Newtonian. And so what you want to do is you want to have a post-Newtonian waveform very early on, and then you have a numerical relativity waveform later on, and you want to match those very accurately. And the problem is that if your numerical relativity waveform is too short, you're forced to do that matching in a regime where post-Newtonian is already starting to break down and get inaccurate. So you really want to have many binary black hole orbits. And one of the questions that we want to answer is how many do you need? And of course that's resolution dependent, that's accuracy level dependent, and we don't really have that answer yet. As far as I can tell, the answer is going to be more than we have already. Another thing that you want to do is you want to be able to handle all of the binary black hole parameter space. So binary black hole has only a 7-dimensional parameter space, which is fantastic for people who are used to thinking about, say, supernova explosions and things like that. You only have 7 dimensions, not many more. You have the mass ratio between the two holes, and you have 6 components of the spin. The total mass turns out to scale out of the problem. If you do a binary black hole simulation of 1 mass, then that entire waveform can be rescaled to a different total mass trivially. You just rescale all the units. So that's why it's only 7 and not 8. And then another thing that we really want is we want automation. We want to be able to run this some numerical relativity code in such a way that you don't need any human intervention, so that and you don't need any fine-tuning, and I'll get to that as well. So let's start with a brief overview of what SpEC is. SpEC is a spectral Einstein code, has this nice little website. The main effort for SpEC has been at Caltech, Cornell, and CITA, and the main matter effort for SpEC has been between Cornell and Washington State. But we are starting to mix in this collaboration, so that there are people who are doing matter at all the institutions and people doing binary black holes at all institutions. And there's a few other individuals as well. I wanted to list the names, but there's over 50 researchers who have contributed to SpEC. So there was I started writing down a list of key roadblocks that SpEC has overcome for binary black hole simulations in the last 6 years, and unfortunately there were too many of them for me to write them down, so I just wrote down a few examples of things that had to be done. And the reason I'm doing this is I wanted to just emphasize that getting SpEC to work was a huge undertaking that took many years and many people's efforts in order to have various pieces work. But I'm not going to go through all of these. I just want to put these up in some selected papers. So how does SpEC work? So what we want is we want to solve Einstein's equations for 2 black holes on some extended volume, preferably all the way out to infinity, but right now we have a finite outer boundary. And what we do is we divide up the 3-dimensional space into a series of finite spatial regions called subdomains, and these subdomains could be of different shapes. One of them might be sort of spherically, like a spherical shell. One of them might be a cube, for instance, or a distorted cube. And what we do is we choose spectral basis functions based on the subdomain shapes. So for instance, in a cube you might choose Chebyshev polynomials in each direction. In a sphere sphere, you might choose Chebyshev and radius and spherical harmonics and angle. And we then solve the equation spectrally, and by doing this you get exponential convergence for smooth problems, as opposed to polynomial convergence, which you get for finite difference methods, and this gives you very high accuracy for smooth problems. One thing that's been added recently by Bayless-Zalagi is that the number of basis functions in SpEC now can change dynamically as the evolution proceeds. This is known as spectral AMR, and this has done wonders for our robustness. So black holes have singularities in the middle. To avoid them, what we do is we excise them. So this is an example of one of our grids, and so this is what we call an excision boundary, which is slightly inside of one of the horizons, and here's another excision boundary slightly inside of the other horizon. And so we do this in such a way that's mathematically well defined and well posed, based on the idea that nothing that's inside the horizon can get out. There's another method that's used by most other groups, which is called moving punctures, and this is basically untested for spectral methods, where there are concerns in this method about smoothness, because spectral methods need smooth solutions in order to converge quickly. So one thing that we had to deal with, and we still have to deal with, is how to excise moving black holes using spectral methods. Spectral methods are set up in such a way that you have to choose your domain first, and it's very difficult when your black holes are moving around to then keep on choosing different domains as you go. Well, what we do is we don't choose different domains as we go. What we do is we use some time-dependent coordinate mapping to map from one basically to map from one shape to another, and so we keep the grid fixed in some grid frame and use this coordinate mapping to follow the rotation and the radial contraction and also the shapes of the black holes. And so we have a feedback control system that adjusts this mapping. One little thing about excision is that it turns out that just being inside the horizon is not good enough for excision. What you have to make sure about is that your excision boundary is actually not a time-like boundary. So for instance, if here's your excision boundary and here's a light cone indicating that everything that's inside the light cone is moving into your excision boundary, into the black hole, this is good. But otherwise, if you have a light cone that looks like this, because your excision boundary is moving too quickly inward, or you have other coordinate problems, then this doesn't work. So in order to solve this problem, we make the excision boundary conform to the shape of the apparent horizon, and we actively control the speed of the excision boundary relative to the horizon. And this control can be quite, it needs to be very finely controlled. So I'm showing you an example here. This is an example in which you have two black holes that are about to merge, and these have a very high spin of 0.95 on each black hole, and you can see the grid is sort of all these little lines, and then there's a green hole and a red hole, and the excision boundary is just barely on the inside of here. And if I zoom in on this, if you're sitting in the front row and you have very good eyes, you might be able to see that the grid just goes a little bit on the inside. I can see it from here, but maybe you can't from the middle of the room. So it has to be very, very finely controlled in order to keep this condition satisfied. Okay, so I talked about grids with two excision boundaries, well, you know that black holes will merge. So what you do at merger is eventually a common horizon forms around both black holes. So here's a picture of this, where here's a grid, and there's a green black hole and a little red black hole, and this gray surface here, I hope you can see that, is a common apparent horizon. Apparent horizons aren't like event horizons. A common apparent horizon will just pop out into existence at some time. And when this happens, then what you do is you stop the simulation, regrid onto a new grid that only has one excised region, interpolate all of your variables onto a new grid, and then continue until everything settles down. Okay. So what are the current capabilities of SpEC? So I want to mention a few things that SpEC can do easily, and I put easily in quotes because none of this is easy. I guess what I mean by easily in quotes is relative to codes that use other methods. So one thing is the high accuracy and efficiency, and that's because of the use of spectral methods. So I already mentioned that a little bit. Another thing that we can do easily is produce initial data with very low eccentricity, and this is by using an iterative procedure that was invented by Harold Pfeiffer and others. Which has also been adopted by other groups, which I'll mention a little bit later. One thing that SpEC can do, again, quote, easily, is evolve a large number of orbits. The largest number of orbits that we have published, in fact, that anybody has published, is 25.5 for some high spin run, and we have a 33 orbit run that's in progress. We're trying to do convergence tests on it. So you can do quite a few number of orbits, and this sort of couples with the high accuracy and efficiency, right? Because more orbits means that you have to spend more time running, and you need much more much more accuracy in order to do it. In fact, doing more orbits, it gets the accuracy requirements get even worse. It tends to get even harder as you do more orbits, harder than you would think. Another thing that we can do relatively easily, again, where easy is in quotes because it wasn't easy at all, is to do large spins. The highest spins that we've done is two black holes with spins aligned with the orbital angular momentum, where each spin is 0.97. And right now Jeffrey Lovelace is running a run with spin of 0.993, which doesn't quite work yet, but that's where we're going next. Okay, so this is what SpEC can do easily. Now let's go to the challenges, the things that I usually don't like talking about. So one challenge is the elimination of human intervention and fine-tuning. So because of the complications of some of the spectral methods, it turns out that a lot of SpEC runs need to, or at least in the past, needed to be finely tuned. So what would happen is, I showed you this picture of the excision boundary and the horizon getting very close to each other. Well, if you don't control that exactly correctly, they might cross, and then everything goes wrong. And you say, oops, I better change some parameter and try again. So this is something that's been a big headache for us compared to other groups. But we've actually been making a lot of progress on that. This is one thing that we're pushing right now, and I'll show you something about this later in the talk. Another thing that's difficult for us, difficult for everybody else too, is to do large mass ratios. And we don't quite understand why it's a little bit more difficult for us. I think it has something to do with the coordinate conditions that we use. It turns out that the smaller black holes seem to get much more distorted in our coordinates than they really should by rights be, just based on the mass ratio themselves. So we're working on a 10-to-1 mass ratio. The largest that's been done to date is 2 orbits of 100-to-1 mass ratio by the Rochester group. But again, I don't think that's routine for them either. So large mass ratios are actually very difficult. So now I want to show a few results, a few things that we've done. So first thing I want to show is an example of a generic binary black hole with spin and precession. And Nick is here. Nick made this movie a few hours ago. So only 2 people have seen this until now. So you have 2 black holes. You could see the little spin vectors on them. And so one thing that you'll notice is that the spin vectors are precessing. The little one at some point was pointing down, and then it was going to point up later, and it's pointing horizontal. The big one is also precessing as well. You'll notice that it starts moving around a little bit more. You could also see very strong spin orbit effects. The entire orbit is now going way out of the plane compared to where it started. And another thing that you're going to see is that, or that you can see, is that there seems to be a kick in this run where the entire system is sort of moving upwards in the z direction. So this is sort of a movie is kind of zooming in, and then you get the merger down to the single black hole. And so thank Nick for doing that movie. So another thing that we've been looking at is event horizons. So we were curious about the topology of event horizons and the structure of event horizons. So there's been several papers in the past, one for instance by Husa and Winokur, that suggest that for a binary black hole collision, that generically you should get a toroidal event horizon for some short period of time. And so we don't see any toroidal phase in our event horizons. Here's a picture of an event horizon as close to the point of merger as we can get. This is for a generic simulation with a 2-to-1 mass ratio and spins of something around 0.4-ish oriented in some weird directions. And you see that you get this strange structure where the little bridge that's joining them is all bent and so on, but we don't see any holes in there. So we don't see any tori. So if you think about what's going on with the tori, the existence of a toroidal horizon depends on 2 things. It depends, one, on how the photons attach to the horizon, and I'll explain a little bit what that means, and how space-time is sliced. So this figure is showing a space-time diagram of a binary black hole, and so here's early times down in the past. Here's one hole, here's the other hole, and they sort of go up, and then they form one hole, and they merge. And what you would see at any instant in time in your simulation is given by one of these slices. So this slice S0 shows 2 separate holes, and then a later slice might show a joined hole. Okay, so what I mean about how photons attach to the horizon is that the event horizon is made up there are several sections to the event horizon. So the part of the event horizon out here is made up of generators, that is photons that are traveling along the horizon, so a photon that's sitting here will continue to remain on the horizon as you go into the future. You see down here there's a little seam. This area here called the crossover area, which is marked as X, that's sort of this strip in the middle. That's made, that section is made up of generators where 2 generators or more even are coming from opposite directions, and they cross right at that point and join onto the horizon. And then these caustics, these are denoted by C. Those are cases where you have generators that are focusing, so nearby generators are coming together onto the horizon. And it turns out that this structure of caustics and crossovers is crucial for whether you get a toroidal horizon or not. One of the key things is that this crossover section here, this strip, is space-like, and so that means that it's possible to have a slice like S1 that dips down through this point P and passes through this crossover thing. And when it dips down through this crossover thing, then you'll have a toroidal cross-section. So that's why I mean that the toroidal horizon depends on how space-time is sliced. Okay, so what we've found in our simulations, we've looked at these crossovers and caustics and so on, and we find out that the photons attach to the horizon in a manner consistent with all the predictions. So they do in the simulations exactly what they're supposed to. They look like they form something like this picture here. However, the slicing that we have does not dip down to this point P, it stays sort of flat, and so it doesn't intersect the torus. So this is why we don't get any toroidal horizons. In principle, a different slicing of our simulations could get a toroidal horizon, but we don't see it in any of the simulations that we've done. And so one question that we have is and we don't have the answer to this, do our gauge conditions somehow preclude toroidal horizons? Something in how we choose our coordinates somehow, even though we don't do it on purpose, chooses slicings that don't dip down like this. Anyway, so this is one of the things that we've been looking at. So
a generic family of slices that don't intersect the torus, or?
Yeah, so there's slices that don't intersect the torus also.
It's a generic family, or?
Yeah. So there should be, but I don't. But there's no. The question is why do you always get slices that don't intersect it, and why don't you ever get slices that do? And we don't know the answer to that. So another thing that we've been looking at, and this is a collaboration between numerical relativists using SpEC and analytical relativists who are trying to come up with new ways of understanding. We have come up with new ways of understanding strong field dynamics. And basically the idea is the gravitational analog of electromagnetic field lines. And so what you do is you define these things called vortex lines and tendex lines, which are streamlines along the eigenvectors of the Weyl curvature tensor, in the same way as you would define electric and magnetic field lines as sort of integral curves along the E field or B field. These are a little bit more complicated just because it's a tensor field and you have to take eigenvectors and so on. But what's nice about these is they have a nice physical interpretation, is that if you're an observer and you're along a vortex line, you get twisted. And if you're an observer and you're along a tendex line, you get stretched or squeezed. And by the way, tendex is a word that was made up by David Nichols here, so which is fantastic. Get your own word in a PRL. So vortex and tendex lines could end on black holes, and we call this concentration of vortex and tendex lines a vortex or a tendex. And here's one illustration of this for a head-on collision. And so you see here, say, a blue area on this. This is an event horizon that has, say, positive vorticity, and so you have, some, I guess now I keep on forgetting whether positive is counterclockwise or clockwise, but it doesn't matter. And these are vortex lines that attach to the other end of this common event horizon, and then you get vortex lines with the opposite vorticity that attach on these on the other end. So this is a case here where you have two black holes that are spinning like this. This guy's spinning down, this guy's spinning up, that are colliding like that head on. And so you can use this red and blue to determine which way the spins are. So in a black hole collision, it turns out that these vortexes and tendexes diffuse and slosh around, and they also generate vortex and tendex loops that travel outward, constituting a gravitational wave. So here is a picture at some later time where you have this sort of pattern of vortex lines that's further out, that's propagating outward at the speed of light, essentially as a gravitational wave. And so this stuff is relatively new, and we've been trying to understand it, and we think that in the end this is going to be as useful for understanding gravitational phenomena as electric and magnetic field lines are for understanding electromagnetic phenomena. Let me give you another example of the vorticity on a binary black hole simulation. So what I'm going to show you here is a case where you have two black holes that have spin down relative to the orbital angular momentum, so this thing on top. And so this is going to be a movie that's being shown in two different directions. This movie was made by Andy Bone, and let me show. Well, before I show the movie, what you see from this side is you see this vorticity indicating that you have a huge spin going down on this guy. So blue is the direction of the spin, going down here and going down here. And in the end, since these are anti-aligned, you're going to have to end up with the spin that's going up. And so the question is, how do these vortex quantities, how does this vorticity change on the horizon? So let me show the movie. And what you see is that even as the horizon starts merging, you already have a blue spot. You already have an opposite vorticity region forming. And the vorticity just sort of sloshes away and then becomes, and then the spin switches direction. Let me show that. Show that again. So it's things like this where you could sort of make local pictures of what's going on, right? You know that at the beginning you have spins down, at the end you have to have a spin up, but here you kind of see in detail at least this representation of how it happens. Okay. So another thing that we've been interested in, and I said something about this on my first or second slide, is post-Newtonian matching. So what we want to be able to do in order to make full waveforms for use for gravitational wave detectors is you want to have some section of a numerical relativity waveform and match it to a post-Newtonian waveform that'll go many, many, many orbits in the past. And so the question is, how well can one do this? So here's a few plots showing a hybridization of numerical relativity with post-Newtonian waveforms for the case of a spin 0.97 on each hole binary where the two spins are aligned with the orbital angular momentum. And this particular run goes 25.5 orbits, which I think is the longest run ever published so far. And what we're going to find is that even for 25.5 orbits, that is not long enough of a run in order to do accurate post-Newtonian matching, at least for parameter estimation. So what this graph shows here is this shows the phase error between different between the numerical results and different post-Newtonian approximates. So all of these post-Newtonian approximates are the same post-Newtonian order. So insofar as the post-Newtonian is supposed to be valid, they should all agree with each other. But they differ in details that essentially put in higher post-Newtonian terms that are unmodeled. So one way to see when post-Newtonian breaks down or when it's inaccurate is to see when these post-Newtonian approximates start disagreeing with each other. And then you know that you probably have to go to a higher post-Newtonian order, or you have to go to a longer numerical relativity waveform, so you go further in the past until those post-Newtonian approximates start to agree. And what you see is that in this region here, the post-Newtonian approximates are forced to agree with the numerical relativity, right, that's where they're fit, so they're forced to agree here, and then you find out that afterwards they disagree very quickly, except for one of them, this Taylor T4, happens to agree very well. This agreement here is basically just a coincidence. There's already other results from other groups that show that Taylor T4 doesn't agree for, say, unequal masses very well. So this is just a fluke, but it shows you how different all of these approximates are. Turns out that you can compute the overlap between these different hybrid waveforms, and the overlap is something like it's bigger than 0.01 if you start going to a total mass of less than 40 solar masses. So this might be enough for detection, but we want to also be able to do parameter estimation, and it, again, depending on signal and noise and so on, we probably need more orbits. I mean, yeah, so sorry, mismatch is what I mean. Yeah, that's what I mean. Sorry. So even this 25.5 orbits is not enough for this particular run. Now again, this run has very high spins, and post-Newtonian formula aren't known quite as highly accurate for high spins, so that certainly has something to do with it. But the thing to take from this is that we may not even now be computing long enough waveforms in terms of the number of orbits. Okay, so now I want to say a little bit about binary black hole waveforms for data analysis. So the big challenges that we have is that even though a 7-dimensional parameter space sounds small compared to other types of simulations, it's still pretty darn big, especially given that each binary black hole waveform takes somewhere on the order of 100,000 CPU hours. Now some of them are smaller, some of them might be 20,000 and so on, but I'm just kind of giving that as a rough estimate. Also, each binary black hole simulation seems to have too few orbits for a complete waveform, and if you want to have more orbits, then you need to increase the number of CPU hours that you put into the simulation. So there's really no hope right now of producing a fully numerical binary black hole template bank. So here's what we do instead. Instead, the idea is to construct some analytical binary black hole template bank based on EOB or based on phenomenological models, and you tune this analytical model using the numerical waveforms. In this way, you can have a very sparse coverage of the parameter space with numerical relativity and still produce we hope, produce a useful template bank by essentially interpolating between all these points with some tuned analytical models. So one organization or collaboration that's doing this is called NRAR, which stands for Numerical Relativity and Analytical Relativity. And this is an international collaboration that includes 19 institutions, 106 individuals, 9 different numerical relativity codes, and 3 template working groups. And its goals, well, 2 goals. One is to produce accurate numerical relativity simulations sparsely spanning a large part of the binary black hole parameter space, and then to produce these calibrated analytical templates covering the entire space. One nice thing about this is that this NRAR collaboration managed to procure 11 million CPU hours on one of the fastest supercomputers around, Kraken, just for doing these numerical relativity simulations. But this 11 million CPU hours is not really enough, so numerical relativity groups are encouraged to use their own resources and add more waveforms. So there are requirements on these numerical relativity waveforms. The requirements are basically on the leading L equal to M equal to mode. Basically, you want the waveforms to be long enough and accurate enough that they're going to be useful. So the length is supposed to be more than 10 orbits, plus merger and ring down. There's a limit on the orbital eccentricity because these are supposed to be eccentricity 0 waveforms. In practice, you don't get eccentricity 0, but you can reduce it to pretty small value. And then there's a restriction on the phase error from the beginning of the simulation to some particular gravitational wave frequency. And then there's also a restriction that if you scale your binary black hole simulation so that the beginning of your waveform is 10 hertz, the beginning of where LIGO is sensitive, then the overlap has to be greater than 0.99 with a particular noise curve.
This is the overlap between multiple resolutions?
This is the overlap, yeah, between multiple resolutions or between multiple extrapolations to infinity with different orders, because sometimes we do that as well. So for everything that enters the the error analysis, that's what the overlap is supposed to be, according to the document that's sitting on the web. Oh, and I also mentioned here, yeah, these numerical waveforms have to be run at multiple resolutions. So when I say that a particular numerical simulation takes 2 weeks to run with so many processors, you also have to remember that you want to run it at multiple resolutions, so it takes even longer than you might think, because you really want to have an error bar on your numerical waveform, and you do that by comparing simulations at different resolutions. You also do that, which I didn't write down here, but there are a few other effects. For instance, you have a finite outer boundary, and you want to you really want to extract what the waves look like at infinity. So what you do is you extract the waves at various radii, and then you extrapolate them to infinity. And so you also have to worry about the error bar on that extrapolation. In the future, we're hopefully going to be able to have waveforms that are evaluated all the way out at infinity. We have 2 ways of doing that. One is this CCE idea that Christian Reiswig is doing, and another idea has to do with hyperboloidal slices that Anil, who's in the audience, has been working on. And that will get rid of one particular source of error in the simulations. So NRAR has been, let's just say it's been difficult. It's been a lot harder than I think people realized it was going to be. And there's several challenges. The biggest challenge for us, for SpEC, and the reason that we were really gung-ho in doing this, because we knew this was a challenge for us and we wanted to try to get around it, is being able to produce many waveforms without fine-tuning. And we wanted to try to use this use this as an excuse to spend time trying to get to get everything automated. Another thing that's been difficult for a lot of other codes is satisfying the length and accuracy requirements, just because it requires a lot of CPU time. Another thing that we didn't anticipate is using this Kraken supercomputer time effectively. There are some, let's just say, suboptimal things about this Kraken machine. For instance, that it's down for 2 days every week, which makes it difficult when you have runs that take several weeks to go. All of a sudden your duty cycle is hitting you. And then there's issues about the Kraken queues, although that again changes in time. Sometimes they're completely empty. And then there's also problems with file systems, is that sometimes you have a run that's going for a week and then you find out some file's corrupted and you have to you either have to do your run over or you have to try to set things up to be able to recover from these things. In addition to these technical challenges, there's been some organizational challenges. So one is agreeing on the length and accuracy requirements. Of course, we have different codes, and different codes have different strengths. So you can get everybody, competing about, no, I want a longer waveform, no, I want a shorter waveform, and so it took a little bit of argument to try to find something that everybody agreed on. Another one is agreeing on the parameters for the binary black holes. So the questions are, so for instance, what we decided to do for the first round of this NRAR is concentrate on mass ratios which are sort of moderate, so nothing, there's no 100-to-1s in there or anything like that. So mass ratios of 3-to-1 or 6-to-1 or something like that, and spins of somewhere around 0.5, no spins of 0.97 for the parameters, because we wanted to make it something that we get a lot of waveforms out of without a huge amount of difficulty. Agreeing on how to measure uncertainties, and this is just something that always happens when you have several different groups come together and they have to come up with because everybody measures their uncertainties in a different way, and we have to come up with some standard so you can compare different codes or different waveforms to each other, and agreeing on data formats and analysis tools. All of this has been it's just taken a lot of discussion, because there's all of these little things that have to be done in order to have a whole bunch of different groups come together and be able to share data and put waveforms in the same repository, and be able to have the people who are doing the analytic tuning be sort of transparent, not care oh, this thing came from SpEC, that thing came from BAM, that thing came from whatever, right? You want it to be transparent for them. So the current status, we have a waveform catalog. There are supposed to be 29 waveforms computed with the Kraken CPU time, 10 of them by SpEC. Out of these, 22 are finished and submitted to NRAR. We have, I already mentioned the mass ratios and spins. There's mass ratios somewhere in, say 3-to-1 to 6-to-1. Nothing more extreme than that. Most of them are low, and the spins of course are also low. SpEC has already submitted 9 additional waveforms using our own resources. And SpEC is planning on submitting more waveforms as they become available, and presumably other groups will as well. But at the moment we have something like 34 waveforms total, or at least we will very soon. Currently, what's going on is that there are scripts being written for consistency checks and for reducing the data. There's everybody's throwing in their waveforms, and there's 30 gigabytes of data, and then you have to figure out, okay, how do you want to organize this data in such a way that people can use it. And then when these consistency checks are complete, the the current plan, although this is still under discussion, is to say, okay, nobody submit anything anymore while groups calibrate templates, although it may be possible that we'll just allow people to submit waveforms continually at any time. It depends on how easy it is for people to say, oh, I did all this calibration, oops, 4 more waveforms were submitted yesterday. We'll have to discuss that. So that's basically the status of NRAR at the moment. There's another collaboration which people probably know about. I'm not going to say much about it at all, just to make sure that people know that it exists and what it does. So this is called NINJA, and the goal is to take existing search algorithms for gravitational waves and to use numerical relativity waveforms as signals and shove them into either real data or simulated data for the first round, real data for the second round, and try to extract them. So currently what's happening in NINJA is that there's a complete waveform catalog with 46 numerical waveforms that obey certain requirements, and a paper about these waveforms is going to be submitted soon. Okay, so the last part is our own little project that we call SPAWN, which is essentially the same thing. This is just a Caltech Cornell CITA project, and we have the same goals as NRAR, trying to cover the BBH parameter space with our own resources. But essentially the real goal of SPAWN is to do what I said we need to do before, is enable SpEC to automatically compute many waveforms at once, without having somebody watch every simulation and say, oop, this one died because of that, let's tweak that parameter. Oops, that one died because of that, let's tweak that parameter. We want all this to happen automatically. All the waveforms that we generate here will be contributed to both NRAR and whatever version of NINJA is around when we finish these waveforms. So I want to mention a little about the status of this. The Inspirals for SpEC are already very well automated, mostly done by Abdul Maroué at CITA, and he's run 125 binary black hole Inspirals, and these have been run at several resolutions, and each one stops with about maybe 2 orbits to go, because that's around where the automation starts getting difficult with SpEC. And so the idea is that we're going in and restarting these from where they left off with new algorithms and new automations. And here are a few histograms that Abdul sent that show, for instance, how many orbits each one of these has. And so they go somewhere from 5 orbits up to 33 is the longest. And these are the mass ratios that go everywhere from 1 to 8. Most of them are somewhere around 2 or 3. Eccentricities are all low. This is the log of the eccentricity, so they're all basically circular, and spins are moderate. They're somewhere in the range of 1/2 for the highest spin. So there's not very high spins in these simulations. And so basically what we've been doing, the procedure is we restart some of these Inspirals from where they all left off, using the same automated procedure and no fine-tuning, and we see what happens. And then when we take a look and say, oh, these died, why did they die, blah, 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 you go back and you repeat refining the algorithm. And so we've made a lot of progress. The first iteration in September, we started 65 of these, and every one failed. So then we decided, okay, we don't want to waste enough CPU time to run 65 at once, so we ran a little bit less at once. But after several iterations, the most recent one, November 7th, we started 25, and only one of them failed. So we're improving quite a bit. We still have the one failure, and what we do is when we have the one failure, we figure out why it fails. We don't go in and tune that one run. We change the algorithm, we run all of them over again, because we want something that's generic and works for everything.
So the mode of failure is the apparent horizon.
Usually the mode of failure is either the apparent horizon hits the excision boundary, or the excision boundary starts going time-like very briefly. So those are the usual immediate failure modes. But sometimes the actual reason for failure might be something different, right? So it might be something like, you know, there's not enough resolution over in this area, and once you lose resolution, it becomes very hard to keep your horizon where you want it to be, or your excision, sorry, where your excision boundary where you want it to be. So, so there's various reasons, but those are usually the immediate reasons. So. Anyway, that's where we are right now with the Spawn project, and I'm out of time, so maybe I'll just stick a summary slide up there and thank everybody for listening to me.
We actually owe you 5 minutes for starting late, so
okay.
A couple of questions.
Yeah.
Under the NRAR, the analytical people use or think about using integral conservation laws. That's what they have.
I don't know, but actually somebody more on the analytical side, I see Ajith right behind you, maybe he knows, right, the analytical ones as far as I know are, there's EOB, is one set of analytical tools, and another one is Ajith's phenomenological templates. But I don't know if...
I have a second question, which you just hit.
Okay.
For someone of a certain age who deals with Medicare, EOB means explanation of benefits.
EOB means effective one body, which is something that Alessandro Buonanno and Thibaut Damour invented, which is basically a way of mapping the binary black hole or binary systems onto an effective Hamiltonian with one body, and you can get actually pretty good agreement with numerical relativity. There are some free parameters that you tune, and so what you do is you tune them by looking at some numerical relativity waveforms. Yes, Christian?
Have you actually tried to compare, regarding this comparison between did you also try this for EOB?
Yes, and we have tried this for EOB, and I mean, we haven't. So what we've done is we've been collaborating with Alessandra, who's the author of EOB, and she's been refining the EOB method, adding new parameters here, refining things there, and so what we've been able to do is come up with EOB models that we tune to several numerical relativity waveforms, and then we try to compare them to similar waveforms that are not tuned, right? And so and that's sort of ongoing. In fact, that's actually what this NRAR thing is all about. It's just that we've been doing that with SpEC waveforms sort of before NRAR started, but we only have a few waveforms. NRAR, we have the whole community that'll be generating many more waveforms for us. But yes, that's But to answer your question, yeah, we've tried that. EOB essentially should match PN again at early times. We haven't done the exact comparison that I showed there, mostly because EOB is much more complicated than PN, and we have to work a lot harder to figure out how to do it right. But no, that's an interesting thing for us to do in the future, is to try matching to EOB very early.
Going to the higher mass ratios, I guess the problem of the standard 5 difference equals a set of resolution that needs to be so small.
Yeah.
You don't have that problem.
Well, yeah, we have that problem. Well, so the problem is it's not only spatial resolution, it's time resolution. So if you have an unequal mass binary, the total mass governs, say, the number of orbits, right? And so if you want 10 orbits, you have to worry about the total mass, but you have to follow the time scale of the smallest mass, right? So it's essentially a time scale problem. It's not just a spatial resolution problem, and so we have that problem as well. You have many more dynamical time scales in terms of the small object in order, say, to get one orbit. Yes?
Do you have to evolve the entire space time steps?
We do now. In principle, you don't have to, and that's something that we've thought about, for improvements later. So what you could do in principle is you could have several levels of grids, and then what you do is you say evolve, say, really close to the black hole, right in the strong field region with a very small time step, and then as boundary conditions you have to take the solution from just outside, interpolate it in time, because you don't have all these time steps. You have to somehow interpolate that in time in order to satisfy the boundary conditions. This is what this Berger-Oliger AMR does. So there's this Berger-Oliger algorithm that does that in time as well as space. Unfortunately, the Berger-Oliger algorithm, which does this well, is second order in time and space. Presumably it could be extended, or something like it could be used to do higher order and to do it with spectral methods, but we haven't done that. But no, that's something that we're thinking about doing, right? Currently, in time, so I mentioned the spectral accuracy in space. In time, we basically use a version of Runge-Kutta that's something like fifth order accurate, and it turns out that our spatial resolution is the dominating factor. So we don't really see this fifth order in time thing, but it's trivial to go to higher order Runge-Kuttas if that's what we want to, if that's what we have to do. But so far we don't. But that makes the entire grid go at once if you put it all on a Runge-Kutta. So we'd have to do something much more different if we want to do what you suggest, which I think is a good idea, but we just don't know how to do it yet. Yeah.
So you talked about comparing to post-Newtonian and EOB. How much do the groups compare codes against each other for certain benchmark mergers, especially for the strong field and the fuzzy ring comparisons?
So that's something that NRAR I didn't mention that, but in the when NRAR, we set up which parameters we're going to do, right? There are certain ones that are repeated for different codes, right? So that so that you have some sort of cross-check. We did do something several years ago, a project called Samurai, where we had several codes where we all ran the same thing and compared them. But which was a great thing. But I think more of that has to be done. But it is built into NRAR, and also in Ninja. I think there's several parameters that are done by more than one code, more than one group, just for a cross-check. I think that's a great idea. You have to do that because, yeah. Oh, thank you.
Refreshments next door.